we're going to go back now to the definition of a vector space, and this is going to be the topic of our discussion for the next few videos. Vector spaces are very important to understand, especially in the scope of data analysis methodologies, because having an understanding of vector spaces allows us to understand how to fit data to different models and things of the like. Not to mention, might I add, that it is pretty much it serves as the foundation for a lot of methods that are used in statistics. So it's very important to understand vector spaces. With this stated, let's go through the basics of what is a vector space. So remember that if we have a set of n-dimensional vectors, okay, such that all of these are in the real numbers, we say that A is a vector space. However, we defined this set of vectors. If two things hold true. For all vectors x1 and x2. Now, I want to be very, very clear about this. I put an arrow here. X1 does not refer to this element. X1 refers to a vector, which itself has elements. So for example, this could be something like x1, 1, x1, 2, so on and so forth. Okay, I just want to be very clear about that so you're not confused, because things can get confusing very quickly if you're not understanding the notation correctly. So x1 and x2 are not numbers. x1 and x2 are vectors. Given any two vectors in a defined set, we say that it's a vector space if I can take any two vectors and the sum of those vectors are also in the vector space. The second condition is that given any k in the real numbers and given any vector in the proposed set, the scalar multiple, the scalar multiple of that vector also happens to be in that set. If those two things hold true about the proposed set A, we say that A is a vector space. Okay. Now let's dig a little bit deeper into this. As it turns out, we can define vector spaces in terms of a generative process. That is, we can define a collection of vectors, a set of vectors, based on some formula or equation that we give. So for example, I could say, let A be the set of all vectors that are scalar multiples and additions of the vector 1, 2. In other words, this is the collection of all x1, x2, such that I have, let's say, Okay, in other words, what I've done is I've just taken the same vector, I've taken scalar multiples of it and added it to itself for all values of k1, k2 in the real numbers. And that vector space looks at like the following, all right? This vector space looks like 1, 1, 2, all right? Remember what we said, any scalar multiples of that vector are also on the straight line. that that vector lies on. So any vector that lies on this line is also in the set A. And if I take any two vectors, scalar multiples of that vector, I'm going to get another vector on that line. How do I know this is a vector space? You could prove it by taking any two vectors from A and proving that I can write it as a scalar multiple or an addition of a scalar multiple of the original vector 1, 2. When we have situations like this, we say that the vector spans the vector space. So in other words, if you're given a collection of vectors, we're defining the span of those vectors. And I'm just going to say 1, 1, x1, I'm sorry, x2, 1, x2, 2, x2, n. And if I have m of these vectors, you know, they're vectors, which I'll by shorthand denote as x1, x2, xm. Okay, the span of these vectors is equal to the set of vectors y1 to yn of scalar multiples of each one. Sorry, 1 and n. Outside represents dimension, inside represents the vector quantity. K2, same thing. Km, same thing. Okay. Okay, so this, if in other words, if you give me vectors, I can generate a vector space by just finding different multiples and additions of the multiples of those vectors. So, for example, let's take, for example, the collection of vectors 1, 2, and 1, 1. Okay. The question is, what is the span of these two vectors? What is the vector space? What is the set of vectors? This is defined as the set of vectors x1, x2, such that I pick any two numbers in the real numbers, and I can write this vector as a what's called a linear combination, which we'll get more into in a follow-up video. And you can rewrite that as k, k1, and 2 times k1, plus k2, k2, which you can rewrite that, of course, as k1 plus k2, and 2k1 plus k2. Okay, so given these two vectors, what I've done is defined a way to generate vectors that are in that space using numbers k1 and k2 from the real number line. So in other words, pick me any two arbitrary numbers, I can plug them into these equations and I can get vectors in the vector space. So the span of vectors is a vector space. Now we're going to get more into the intricacies of this, not at the moment in time. But when we get to linear dependence and independence, what we'll see is that vector spaces can be expressed more compactly based on just defining the vectors that can generate that space in the first place. We'll get to that at a later video, but hopefully you grasp the concept that if you give me one or more vectors, I can generate new vectors from that. If you're having difficulty thinking about that, all right, think about it. If I have a vector, just one vector, and I'm curious, what is the span of the following vector? 1, 2. Okay, so I'm out 1, I'm up 2. Well, okay, 2, 2. What is the span? Well, what is the span? Remember, the span is the collection of all vectors such that I can write it as an addition of scalar multiples of each vector. Well, I only have one vector in here, so this is just simply the scalar multiple of that single vector. But notice that I have scalar multiples of that vector, which we said in an earlier video that a scalar multiple of a vector is just that vector extended, contracted, or reversed. So if I'm doing this for all k in the real number line, then I'm talking about any point on this line. So as it turns out, the line is a vector space because it's a collection of vectors such that when I add them together, I get another vector back in the space. And when I take scalar multiples, I get vectors also back in the space. You'll notice, however, that there's some points that are in the vector space that are not, some points that are not in the vector space. And that, for example, this point, there's no way that I can take 2 or more vectors in here and combine them together with scalar multiples and addition to get up here. You try to find me that. You know, take any vector like this black vector here, for example. Can I, you know, multiply? If I think about it, if I multiply, I'm only extending this in the same direction. If I take 2 of these and I add them, again, because they're in the same direction, I'm still in the line. There's no way I can change the angle to get that point. It's impossible. To do that, I would need another vector. So if I have 2 vectors like this, then that's possible. Yeah, I can find a K1, K2 to be able to possibly get that. Now the number of vectors. So this is here's the net of everything that I want you to take away from this lecture, this video. Vector spaces are sets of vectors, and we can think about them in 2 ways. The first way is to start with a collection of vectors and use those to generate the collection of vectors. Most of the time, however, we start with a collection of vectors and we want to find out which vectors can be used to generate all the other vectors. For example, if I take any vector, the set R2, right, which is just the set of all vectors, where x1, x2 are in the real numbers. The set of all vectors like this can be generated using only 2 vectors. This is the span of the vectors 1, 0 and 0, 1. Think about it. All I need to do to get these 2 is write this as a linear combination, right, of the number x1 times 1, 0 and add that to x2 times 0, 1. So I can use, and x1 and x2 are any real numbers. So I can use these 2 vectors to generate all possible vectors in this space. in this case, we went from starting with the set, namely R2, and trying to figure out what are the collection of vectors I can use to generate all the other vectors. On the flip side, if I were to start you off here, the question is, well, what's the resulting vector space? What does that look like? The number of vectors that are used to generate the space is what's called the dimension of the vector space. In this case, we have a dimension of 2. In this case, we have a dimension of 1, because one vector is used to generate the whole vector space of the line. There's a theorem that says if the dimension of a vector space A, let me take a step back. If A is a subset of B, if the dimension of A, of the vector space A, is equal to the dimension of the vector space B, that is, if the number of vectors that are used to generate A is the same as the number used to generate B, then it's true that A equals B. More specifically of the real numbers. So that's true. Notice this is dimension 1. It's a line. It doesn't cover the whole plane. The dimension of this is equal to 1. The dimension of the real numbers, as we just illustrated before in the plane, is equal to 2. I use 2 vectors to generate those. One thing that needs to be very important, one important thing that needs to hold true about these vectors, by the way, which are used to generate the space, is that they are linearly independent. And we will discuss that in the following